Today we're going to look at our last law of inference, and this is called the Law of Syllogism. And the Law of Syllogism deals with two conditionals, unlike the Law of Disjunctive Inference and the Law of Detachment. Okay, so let's look at the do now, which is an illustration. Suppose I said, if it rains, then I will go to the movies, and that's a true statement. And also, if I go to the movies, then I will buy popcorn is also a truth statement. Well, it would seem logical that the following conclusion can be formed. If it rains, then I will buy popcorn. So the law of syllogism deals with the following. If two conditionals are true, and the consequent of one conditional matches the antecedent of the second, then they cancel and the resulting conditional is true. So let's write it out in symbols. So let R represent it will rain. And let M represent I go to the movies. And let P represent I eat popcorn, or I will buy popcorn. So symbolically, we could say, if R, then M, for the first statement. If M, then P, for the second statement. And therefore, because this is given and they're both true, and this is all implied, it's understood, and there's that invisible word and in between them, then we can conclude that if R, then P. So these kind of cancel. All right, so let's write the law of syllogism out in terms of P and Q. So the law of syllogism is very hard to state in words. It's easier with symbols. If P then Q and if Q then R, then we can say if P then R. Okay, so let's prove this. And we're going to prove that if P then Q and if Q then R, which is the given or the antecedent of our conditional, which is the given, then we can conclude if P then R is a tautology. And this would be a very nice way to prove the law of syllogism. So let's set up a truth table. Notice that we have 3 simple statements. So our truth table will have 8 rows. So let's build it up together. Okay, I've set up the headings for you. And we start with our simple statements P, Q, and R. Then we have if P then Q, we have if Q then R, and then we form the conjunction between them. And then finally, I should have put a column for if P then R. So let me correct that. Okay, so we have a column for if P then R, and then finally putting everything together. The antecedent, which is this column, and the consequent, which is this. All right, so let's fill in this truth table. Let's remind everyone that we start with 4 truths and 4 falses. And then the Q's are 2 truths and 2 falses alternately. And then the last statement is an alternate true-false, always. And remember how we compute that? We know that the number of rows in the truth table will be 2 to the number of simple statements. And that would be 2 cubed, which is 8. And in this case, we just divide by 2 and then divide the 8 by 2, we get 4. Divide the 4 by 2, we get 2. And divide the 2 by 2, we get 1. All right, so let's just try to line these up because it's going to be a pretty long truth table. Okay. All right. So let's fill in the first column, the conditionals, which are easy. So a conditional is false when its antecedent is true and its consequent is false. So we see that instant here when we have a true and a false. That would be false for if P then Q. The other ones, when P is false, this will always be true. So this is, and also here, we have a true and a false. So those 2 rows would be false, and everything else is true. Now, if Q then R, okay, again, the Q is true and then false here. And we also have a true here and a false there. But everything else looks like it's true. So let's put that in there. So this is a false, and this is a false. And then all the others are trues. Okay. And I'm going to jump over to the if P then R column. So I'm looking at the first column and the third column in the beginning. I'll circle that in blue, or maybe in red. That would be easier. So here for if P then R, I've got true, true for the P and the R, a true, a false. So that would be false. A true, true, a true, and a false here. And then everything else, when P is false, the conditional is true. So I have a false on the second row and the fourth row, but everything else is true. Okay. Now let's form the conjunction between these 2 columns. And we know a conjunction is true when both conjuncts are true, which happen to be conditionals. So that would be here. Not here, not in the second one, not in the third one, not in the fourth one, in the fifth one, not in the sixth one, but also the last 2. And everything else would be false. All right, now we combine these last 2 columns so that this is our antecedent here. This is our antecedent, and that's our consequent. So let's see. If true, then true gives me true. If false, then false is true. If false, then true is true. If false, then false is true. If true, then true is true. If false, then true is true. If true, then true is true. And if true, then true is true. Yes, a tautology. So we proved the law of syllogism. There it is. All right, let's copy these 5 problems down, and let's see how we could use the law of syllogism to make a conclusion if we can. All right, so let's start with number 1. If A then H, and we're given if H then G, then the answer would be if A then G. By the law of syllogism, they cancel. Similarly, in number 2, the answer is if F then E, we can apply the law of syllogism. But in number 3, we don't have the matching pieces in the right place. We can always write this below. Since a conjunction is commutative and there is an invisible word and now when we cancel, we get if A then B. So the law of syllogism does apply if we have this situation when they don't cancel from right to left. We could always cancel from left to right, but we keep the order of the conditional. So we have if A then B. Now, in number 4, we use the law of syllogism twice. From these 2, we conclude if A then C, and then combining it with the if C then D, we conclude if A then D. So that would be our final conclusion. And in number 5, it doesn't look like we could use the law of syllogism directly. We do not have a match, but using the law of the contrapositive, this becomes the negation of Q, then not P, and then if not P, then R. And notice that these would cancel, and we can rewrite this as if Q, then R, since not Q is logically equivalent to Q. All right, now let's take a look at some logic proofs. So I wrote one out here. Given if A then S, and given if S then N, and given not W or not N, and given A, so we have 4 givens, prove not W. All right, so now some students are able to combine these right away to get to the proof. Sometimes it's better to kind of take a look at the statements and see which ones you could put together automatically. And notice that what we can do is looking at the first 2 statements, we can use the law of syllogism. So let's take a look at that. Let's start writing it up. One. So if A then S, and if S then N, reason, these are all given. Three. All right, then we conclude if A then N by the law of syllogism. Using steps 1 and 2. All right. Now, the only other given I could write after this is A, because that's what we have. A is given. So from steps 3 and 4, we can use the law of detachment, which is N. And that's from steps 3 and 4. Okay, so we used A, so we'll check that off. Now, the only thing we did not use is the not W, the not W or not N. So let's write that down. And the only law that's left is the law of disjunctive inference. That's the only one that we can use with the disjunction. But we have to show that we're negating one of the disjuncts. And the disjunct that we're negating is N, and we did. So, well, actually, we should write down number 7. We're negating the second disjunct. right? This disjunct. And that is, okay, so this is given. And this is the law of double negation. Which is from step 5. And then finally, not W, from the law of disjunctive inference. Steps 6 and 7. But that's one way to prove it. There's another way. And what we can do is, if we take the if A, then S, which is given, and the A, which is also given, we can use the law of detachment right away to get S. In steps 1 and 2. And then we could write the second conditional, if S then N, and that's given. And we could detach again to get N, which is the law of detachment. Steps 3 and 4. And then after that, the proof has to be the same. So here I would say same steps 6 through 8 as above. So notice that as the proofs get more complicated, there's more than one way to do them. Let's look at another. Okay, now this proof is a little bit more complicated because we're given words. And the first thing we have to do is translate these words into logical symbols so we could easily use our laws and axioms. So let's take a look at the given. If Lynn is good at swimming or good at soccer, then she is a genuine athlete. If she drinks a pint of grapefruit juice every day, then she is good at swimming. If she does not drink a pint of grapefruit juice every day, then she is not good at logic. However, Lynn is good at logic. So we want to prove that Lynn is a genuine athlete. And these letters represent the corresponding simple statements. S would probably mean that she's good at swimming. O would probably mean she's good at soccer. A would probably mean that she's a genuine athlete. G would probably mean that she drinks a pint of grapefruit juice each day. And L would probably mean that she's good at logic. So all these letters represent the affirmative case. So let's rewrite the given in symbols. So if Lynn is good at swimming, that's S, then, oh wait, there's more, or good at soccer. So let me correct that. So if she's good at swimming or soccer, so I guess that would be S or O, and this is the antecedent, then she is a genuine athlete. Then A. If she drinks a pint of grapefruit juice every day, so that's if G, then she's good at swimming. Well, that's S. If she does not drink a pint of grapefruit juice a day, so we have to negate this. So if not G, let me just write the same, not G, then she's not good at logic, not L. But she's good at logic, L. And we want to prove that she's a genuine athlete, which is A. All right. Now, there are several ways to approach this, and let's see what we have. A good way to approach this is to begin working backwards. This is a nice strategy if you don't see it right away. And okay, so let's try it. and again, this is an optional step. We want A. We start with what we want to prove, and we pick the statement in the given that has A. And we know S or O, then A. So now, to get the A by itself, we've got to get this. We need S or O. Now, we haven't discussed this, but if S is true, if we could get S to be true or O to be true, if we could isolate either one of these, then the disjunction is true. So we need either an S or we need an O. And if we could get one of those to be true, then we could combine it and get S or O is true because of the axiom of the disjunction. All right. Well, it looks like we're going to get S. It looks like to me that we're going to get S because O appears once, whereas O appears once and S appears once. So maybe we can't tell. Let's see. All right, so we'll put this conditional aside and we'll take a look at the remaining given. We know if G then S, and we know if not G then not L. So what we can do, in order to use the law of syllogism, we could form the contrapositive of any of these two. Let's form the contrapositive of the top one because it seems to be easier. We don't have to use the law of double negation there. And now we see that these would cancel and we would get if not S, then not L. Okay. However, we're given L. So again, it seems that we would have to take the contrapositive of this, put L together, and conclude S. So now that we've got S by itself, we could get S or O to be true, and then finally detach from the first conditional. So if we number our steps, okay, we number our steps. Let's see. Well, we would have to put them in logical order. So I guess we would start with there are lots of ways to go. We could detach. We could also use the law of detachment. We could use the law of syllogism. We use the law of syllogism. So let's try to put them in that order. So why don't we write the following? All right, so we'll begin. Statements and reasons. So now we have a dilemma. What would go first, according to our outline? Well, we got S from given L and if L then S, which came from if not S then not L, which came from the law of syllogism above. So it would make sense to start with these steps. This one and this one, which are both given, then take the contrapositive of either one, and it doesn't matter, except that if we took the contrapositive of the second one, we would use the law of double negation, and the proof would be just as long. So let's do it the way we did it. So this is 1, 2, the contrapositive, the law of syllogism, the contrapositive, and then L, and detach. Okay, so those would be our first 7 steps. So let's do it. So we'll say if G then S given, and if not G then not L, which is also given, then we took the contrapositive of the first one, if not S then not G, law of contrapositive, on steps 1, right? This is step 1. And then we using these two, the law of syllogism, and got if not S, then not L, law of syllogism, in steps 2 and 3. Then we took the contrapositive of that. I guess we have to do double negation anyway. If not L, then not S. And this is the law of the contrapositive. Step 4. And then we have if L, then S. And that's the law of double negation. Step 5. And then we put down our L, which is given, and we detach to get the S to be true. And this is the law of detachment. Steps 6 and 7. And if S is true, we could put it together with any other simple statement, whether it's true or false. We could put it together with A, we could put it together with G, we could put it together with L, but for our purposes, we want to put it together with O so that we will get the antecedent of the first conditional. So we write if S or O is true. Oh, gotta get this. And the reason is a disjunction is true. Okay, let me just erase this thing here. I don't know where this came from. A disjunction is true when one of its disjuncts is true. Of the disjuncts is true. It's the axiom for a disjunction. This is the axiom of a disjunction. Just like the law of simplification is the axiom for a conjunction. And then finally, we'll write the given S or O, then A. That's given. And we have finally A, the law of detachment. Because S or O is the antecedent of that conditional in step 10. So it's steps 9 and 10. And we completed the proof. I'm sure there are other ways to do it. Perhaps there's a shorter way to do it. If we took the contrapositive of if not G, then not L, maybe it would have been quicker. Maybe we could have just used the law of detachment and avoided the law of syllogism, but we do get the same result. Let's take a look at one more proof. I would like to do a proof with you involving De Morgan's laws, and we could tell that we're going to use De Morgan's laws as soon as we see the negation of a conjunction or disjunction. All right, so copy this down and see if you could write a statement reason proof for this, and we'll go over it. So to proceed with this proof, sometimes, and a lot of students just write all the given in the statement column because we have to use the given eventually. But it's nice to put the given together so we could make a conclusion. So let's start with the two conditionals, since we're talking about the law of syllogism, and write them down. And that's given. And immediately we conclude if B then H by the law of syllogism. In steps 1 and 2. Okay, so we use those two. All right, now we're going to put that aside. We'll save it, and let's go to the next given. Well, I can't do anything with the A yet, but I could rewrite this given. Apply De Morgan's laws by negating each conjunct and changing the conjunction to a disjunction. And this is De Morgan's laws. on step 4. And of course, we simplify this to not A or B. And this is law of double negation. So notice that the law of double negation is used with De Morgan's laws, with the contrapositive, and perhaps the law of disjunctive inference if we wanted to show the negation of a disjunct. All right, now we've got the A. We could put that in there. And we have to show that A is the negation of not A, the first disjunct, law of double negation. Oh, I forgot to put down step 5 here. So this is the law of double negation. Step 7. And then finally, we could conclude B by the law of disjunctive inference with steps 6 and 8. But we still have to prove H. So going back to this step, if we put if B then H is true and B is true, we have a true conditional and its antecedent is true. We conclude H by the law of detachment using steps 3 and 9. Okay, and that completes our proofs for today. All right, so to summarize, let's summarize our laws. To summarize, we've learned the law of syllogism. This was our new law. If P then Q, and if Q then R, then if P then R. It could also be written this way. If we reverse them, since and is commutative, we cancel either this way or that way. We still end up with if P then R. Okay, but 2 conditionals have to be true to use the law of syllogism. The other 2 laws that we talked about, the law of detachment, also involves 1 conditional, but the antecedent must be true to conclude the consequent is true. And in another law, the law of disjunctive inference, this one confuses students a lot because you deal with a true conjunction because of the disjunctive, a true conjunction, but one of the disjuncts has to be negated. Oh, wait, Q, not Q. Then the other disjunct is true. Oh, wait, I wrote this wrong again. This should be Q, and this should be P. Okay, so with the law of detachment, we have a true conditional and its antecedent true, a single statement that's true. For the law of disjunctive inference, we have a disjunction that's true and a single statement that's true, but negated. Okay, so those laws are new. And then the other laws that we've discussed through truth tables were the law of double negation, if we have P, then that's logically equivalent to not P, and vice versa. We've got De Morgan's laws, which has its 2 parts, the negation of a conjunction or the negation of a disjunction. So that's equal to, it's like distributing the negation, but we have the opposite connective. This becomes or and that becomes and. Then we have law of the contrapositive, which says that any conditional is logically equivalent to its contrapositive, flip and negate, remember the little dance. And then finally, we've got the axioms that we can use. Okay, we've got the axiom of the conjunction, also known as the law of simplification, that says if a conjunction is true, let me just write the conjunction. I can't write letters anymore. If P and Q is true, then we could take out the P or we could take out the Q. And then there is another axiom for the disjunction, which we used in one of our proofs before. And this does not have a name. It says that if P is true, then P or any other simple statement has to be true. And that takes care of our laws. So notice that all the laws on the right involve one given, whereas the laws on the left involve two givens. So in order to use the laws on the left column, we have to have these two given statements within our statement proof, within the statements of our proof. All right, that takes care of proofs for today. We'll practice more next time. Have a wonderful day.